Kino, Science, Technology and Design Insights. Size of computers and technology are a big deal. Just taking a look at Apple, one of the major selling points of the iPhone 6 is that it's only about 6.9mm thick. Each year we manage to make our devices smaller and smaller, and there's a theory to describe this: Moore's Law. Moore's Law observes that the number of transistors in a dense integrated circuit has doubled approximately every 2 years. In simple terms, this means that every 2 years we can pack twice as much memory into a device, or make it half the size and hold the same amount of information. Just think about what your phone looked like 5 years ago. Yeah. So assuming our advances in science and technology continue, and we do manage to keep packing more and more into our digital electronics, surely there's a point when you can't get any smaller. There's only so many transistors you can fit onto the area of a circuit board, right? Looking at where we are now, the latest Intel computer chip or microprocessor has transistors that are about 14 nanometers in size. The building blocks of transistors, silicon atoms, are about 1/3 of a nanometer. So we're really pretty close to the limit of traditional computers, and we won't be able to go much smaller. Scientists are all too aware of this, and so are looking at alternative solutions, one of which is quantum computing. So what on earth is a quantum computer? Well, it's built on the basics of quantum mechanics. Stay with me here. And it's not that different to a current digital computer. A current digital computer is built using Boolean logic, named after George Boole, and this logic describes a way of analysing switches in circuits, either as on or off, and allows complex problems to be solved relatively easily. Quantum computers are based on the same Boolean logic used in current computers, except that instead of having just ones and zeros, on and off states, a quantum computer would allow you to have a state in between the 1 and 0, which is called a superposition. You can think about it in terms of colour. Instead of just having black and white options, you've now got everything. It sounds like a small change, but the difference in processing power you'd get from doing this is huge. The difficulty with quantum computing is that the results are not always certain, as dictated by Heisenberg's uncertainty principle. With current technology, results are certain. The switch is either 1 or 0, on or off. But with quantum computing, it's difficult to tell how far on or off the switch is. You just know it's somewhere in between. This is called quantum fuzziness, and it's a real issue for scientists. The solution to this fuzziness problem is to repeat the measurement multiple times, and that way you can get a higher probability of knowing the position of the switch. Of course, it's all a lot more complex than that. As you try to encode and process information on a quantum system, the atoms need to be kept still. The higher the temperature of an atom, the more it moves about, and so to get any useful output, the atoms need to be kept at about 1/1000th of a Kelvin. This is roughly minus 273 degrees Celsius. On top of that, as you start to compute, the atoms heat up and produce noise which also needs to be addressed and kept below a certain threshold. Scientists estimate this technology will start to have major impacts on our everyday lives in about 20 plus years, so there's still a long way to go. For more science, technology and design insights, check out my Instagram, @Kino.